Hi everyone, I'm Akelo Fatuma Kedrin from Uganda. Part 1, we shall talk about implementing a stack with a linked list. To implement a stack with a linked list, we map the top of the stack to the head of the linked list. A stack follows the LIFO, last in, first out principle, meaning the most recently added item is the one we need to access and remove the fastest. By using the head of the linked list as the top of the stack, we ensure we can ensure that adding and removing items happens to the very front of the list structure. The first part is push. Then how it works, the push operation corresponds to inserting a new node at the head of the linked list. We create a new node, point its next reference to the current head, and then update the head pointer to point to this new node. Then time complexity, the O into bracket 1 meaning constant time. Since we have direct access to the head of the list, we don't need to traverse the list to add the item. It happens instantly regardless of the stack size. Then 2, we have pop. How it works, the pop operation corresponds to removing the node at the head of the linked list. We retrieve the data from the head node, update the head pointer to point the next node in the list, and effectively discard the old head node. Then time complexity, the O into bracket 1 constant time. Just like with the push, we have direct access to the node that needs to be removed. We simply update the head reference and return the value. Then 3, we have the get top into brackets or pick. How it works is that this operation simply looks at the data contained within the head node of the linked list without removing it. Then time complexity is the O into bracket 1. We access the data property of the head node directly. Then 4, easy, that is empty. How it works is that we check if the internal head pointer is null. Then time complexity is the O into brackets 1. This is a simple Boolean check on a single variable. Then our part 2 is implementing a queue in a linked list. To implement a queue using a linked list, we need to leverage both the head and the tail of the list. A queue follows the FIFO, which is first in, first out principle. To make this efficient, we map the head of the list to the front of the queue where items live, that is into brackets, and then the tail of the list to the back of the queue where the item enters. Then our first is NQ. How it works is the NQ operation corresponds to inserting a new node to the tail of the linked list. We create a new node and update the next pointer to the current tail to point to this new node. Then we update the tail pointer to point to the new node. Then the time complexity is the O into brackets 1 constant time. Because we maintain a reference to the tail, of the list, we can add items to the end immediately without ending the traverse from the front. Then 2, we have dequeue. How it works. The dequeue operation corresponds to removing the node at the head of the linked list, into brackets, the front of the queue. We retrieve data from the head node and update the head pointer to point the next node in line. Time complexity, the O into brackets 1, which is the constant time, we always remove the from the front, which we directly access to via the head pointer. Then 3, we have size. How it works is that to determine the size using a standard linked list without a counter variable, we must start at the head and traverse through every node using the next pointers until we reach null, incrementing a counter along the way. Time complexity is O into brackets n, meaning linear time. In this worst case, where the dequeue is not empty, we must visit every single node in the list to count them, into brackets. Note, if we maintain the integer count variable that updates on every NQ and DQ, this could be O into brackets 1, but strictly using the linked list node requires traversal. 4 is empty. How it works is that, similar to the stack, we check if the internal head pointer is null. Then time complexity is the O into brackets 1, which is constant time. This is simple Boolean check on every single variable. Thank you.